All right, let's get right into it. When you're designing a database, you have to decide, do you make these really wide tables with tons of columns, or do you break things up into smaller, narrower tables? It feels like a simple choice, but the impact on performance, well, it can be absolutely massive, and maybe not in the way you'd think. You know, there's this piece of advice you hear all the time, even from really smart folks. The idea is that one-to-one relationships are just a waste of time. If data is closely related, just mash it all together into one big table. Keep it simple, right? But is it really that simple? Is that common wisdom actually a good idea when the rubber meets the road? Well, that's what we're here to find out. We're going to put this whole one big table myth to the test, and trust me, the results are pretty eye-opening. Okay, so let's dig in. We're going to set up an experiment where we take that advice to heart. We're going to build a system around this idea that one giant table is the best way to go and see what actually happens. So here's the setup. On one side, we have our wide table. Think of it as this monster employees table with everything thrown in. We're talking over 45 columns. Name, salary, contact info, you name it, it's in there. On the other side, we have our narrow table setup. We took that exact same data and split it logically across 4 separate, clean tables. And to keep things totally fair, both sides are loaded with the exact same 1 million records. And the query we're going to run, it's super simple. Nothing fancy. Just, hey, give me the first 20 people hired in the HR department. We only need their ID, first name, and last name. That's it. A totally normal, everyday kind of query. All right, drum roll, please. We ran the query against both setups. And this is where that whole one big table idea really starts to show its cracks. Let's check out the results. Whoa, okay, look at that. The wide table clocks in at around 276 milliseconds, but the narrow tables, just 122. That's more than twice as fast. But honestly, that's not even the craziest part. Look at that second line, the pages read from disk. That's the real bombshell. 142,000 pages. That's what the wide table had to pull from the disk. The narrow tables, under 9,000. That is just a staggering difference. And you have to remember, reading from the disk is the absolute slowest thing a database can do. It's the ultimate bottleneck. So what the heck is going on here? Why we only asked for 3 little columns, but the database ended up doing all this crazy extra work? To figure this out, we've got to pop the hood on Postgres and see how it actually works. To really get what's happening, we need to understand 2 core concepts: how Postgres physically stores data and how it handles changes to that data. This is where we get into pages and versions. So first things first, pages. Postgres doesn't grab one row at a time from your disk. It reads data in these fixed 8 kilobyte blocks called pages. Every single time Postgres has to go to the disk, it comes back with a full 8 KB page. No exceptions. Now think about our giant wide employee table. Each row is huge, so you can only fit a few of them on a single 8 KB page. This means when we ask for just the names of some employees, Postgres has to go fetch a page. And that page is loaded with all this other junk we don't care about. Salary data, performance reviews, all 45 columns worth of stuff. It has to wade through mountains of irrelevant data just to find the 3 columns we actually wanted. Okay, so that's part of the problem, but it gets worse. The second piece of the puzzle is something called MVCC. It's a really clever system, but it has a side effect. The key idea is this: when you update a row, Postgres doesn't erase the old data. Instead, it creates a whole new version of that row. So let's say you update an employee's phone number. Postgres makes a full copy of that entire 45-column row, changes the phone number, and then marks the old version as dead. But here's the kicker. That dead row doesn't just disappear. It sticks around, taking up space on the page. We call this table bloat. And over time, your pages get filled with these dead row ghosts, which means even fewer useful live rows can fit on a page. It's a vicious cycle. Now, I know what you're probably thinking. Okay, I get it. It's slow. Just add an index on the department column. Problem solved, right? It's the classic fix for a slow query. But is it really going to work here? So we did it. We added a standard index on the department ID column. And the result? The query was actually a tiny bit slower. I know, right? The PostgreSQL planner basically took one look at our index and said, nah, I'm good.
And then it just went ahead and did a full table scan anyway, reading all 142,000 of those pages all over again.
So why in the world would it ignore a perfectly good index? Well, it all comes down to a thing called selectivity. In our data, the HR department makes up about half of all the employees. For the query planner, using an index to go and find half of all the rows in the table is actually more work. It's like using the index at the back of a book to find every single page with the word "the" on it. At some point, it's just way easier to read the book from cover to cover.
And let's be clear, this wasn't about using the wrong type of index. B-tree, hash index, it doesn't matter. They're designed to find a few needles in a haystack. If your query is asking for half the haystack, the index just isn't the right tool for the job. You've got a much bigger, more fundamental problem with your data layout.
And look, Postgres is an amazing database. It has all this powerful stuff like streaming replication for high availability, but you have to remember that even the most advanced features are built on top of a foundation. They can't magically fix a bad schema. If your main database is choking because it's reading 100,000 extra pages, all that replication does is make copies of a database that's choking. It all comes back to a smart, efficient schema design.
So after all of this, what's the bottom line? What's the big lesson we can take away from this deep dive into Postgres performance?
It's this: you have to design for how you're actually going to use your data. That advice to just jam everything into one table can be a performance disaster. What we've seen is that splitting your data into narrow tables can be a huge win. Put the stuff you query all the time together in a lean, efficient table. And all that other stuff, the big text blobs, the data you barely touch, move it out into its own table. It might feel like more work up front, but it can save your database from a mountain of pointless work. So I'll leave you with this one question to think about. Look at the application you're working on right now. Are your tables built to help your queries? Or are your queries constantly forced to fight an uphill battle against your schema? Really thinking about that might just be the thing that unlocks the performance you've been looking for.